So obviously we've had a lot of discussions about public blockchains over the last couple of years, and then public blockchains have been refashioned to become private blockchains. And I guess where we're at next is that there will be an interaction between the two, is the obvious kind of move forward. So Dominic's about to present the project that he's working on, CTO at DFINITY and String Labs as well. And that is the issues that are going to address from the ground up. Some very interesting ideas. So I will hand over to Dominic to tell them more.
Thank you. Hi, yeah, so I'm here to introduce DFINITY. DFINITY is not a cryptocurrency, it's a blockchain computer. So it's mainly concerned with processing computations in a way similar to Ethereum, but with some different properties. The kind of overall vision is to create a decentralized cloud, which, if you like, is an infinite blockchain computer we can do various things with. And it has some unusual features. It's got a kind of governance layer called the blockchain nervous system, which we'll cover. So the basics, DFINITY is a kind of performant blockchain computer. And that means that transactions are finalized much quicker than we see transactions finalized today on proof-of-work networks. So we're looking at finalization in sort of 3 to 7.5 seconds on average, which is a big speed up. That's more than a 50x speed up than what you see today on Ethereum with the Ghost protocol. We'll cover how that's done a bit later. But this is a big step forward because it means that you can create applications where the user is very concerned about the state, for example, like a financial market, in ways that you can't really do today. And if you created, for example, a financial market over Ethereum, you might be able to maintain a market order book on the chain, and you might be able to display that with a DApp interface. But you'd have to find a way of conveying to the trader that, once they've submitted an order, even though it seems that that order has settled in the book or executed, in fact, the book can be reorganized and the trade reversed for several minutes, right? So Bitcoin finalities, kind of 6 confirmations, sort of 60 minutes thereabouts, right? Can be much longer, can be much less. Ethereum's sort of 10 minutes today, about 37 confirmations, I think. So bringing that down to just a few seconds is a big, an important step forward. Talking about producing an infinite blockchain computer, and we'll come back to how the project started, but this was one of the original objectives. So what that means is that as new miners join, the capacity of the network actually increases. And this is very different to today's networks where the performance and the capacity of the network generally stays the same as we increase the number of participants, but there's no way of increasing the capacity. This is another thing we've done. We've tried to introduce sort of intelligent governance without introducing intermediaries. And we've got this thing called the blockchain nervous system. And if you want a way of thinking about that, today we have the code as law, right? And this is trying to introduce the AI as law, right? Different kind of paradigm. So research on DFINITY sort of began January 2015. The original objective was just to create a sort of infinite blockchain computer which addressed the performance challenges. The envisaged uses of the decentralized cloud, on the one hand, were creating sort of open tech intermediaries. That's things like a sort of decentralized Uber, even web search. The idea that you could create a decentralized Google was one of the driving objectives behind the research. And at the other end of the extreme, we wanted to be able to enable sort of re-engineering, widespread re-engineering of corporate systems to make them more efficient. So just so you can understand more about where we are and where we came from, there was a project in 2014 called Pebble that was focused on enabling sort of micropayments over cryptocurrency, not with some kind of lightning solution, but with on-chain scaling. And that basically folded into the DFINITY project in 2015, which was pursuing infinite blockchain computer ideas and seeking to achieve that by applying randomness that's generated by cryptography, right, rather than by puzzle searches in proof of work. Last year, there's a company in Palo Alto called String Labs, which is a kind of investor incubator studio for open protocols. It incubated the DFINITY project. DFINITY Stiftung was created, which is a not-for-profit foundation in Switzerland. February, there was a kind of seed fundraising. As a consequence of that, DFINITY Stiftung has about $10 million in assets for R&D, which is nice to have, obviously, and we're scaling out the team at the moment. The next steps are the launch of a test network, which will demonstrate threshold relay and the blockchain nervous system in sort of basic form. And then after that, there'll be another fundraising, which is hard capped at 20 million Swiss francs. And these fundraisings run autonomously on Ethereum using smart contracts. So this is how we see the Ethereum virtual machine ecosystem. So at the moment, you've got a kind of stack where you've got the Ethereum network. It's the code is law, managed by the community. We've got this Casper system coming, which favors what I'd call extreme availability. And on top of that, you've got this open standard, which is the Ethereum virtual machine, upon which you can build decentralized applications. So, we see that being broadened out by DFINITY, acting as a kind of sister network, which will have some key differences. So instead of the code as law, we'll have the AI as law. And instead of Casper, we've got these new protocols, which we refer to as Crypto 3, which optimize for performance and scale. So, in pursuit of the dry, don't repeat yourself, we're trying to extend the ecosystem here. The code as law is preferable for very many decentralized applications, right? And similarly, many fiduciary applications may prefer extreme availability. We're providing a very different kind of environment, and of course, the AI as law produces a completely different kind of platform to the code as law, and in many ways it turns a lot of preconceptions about what makes a blockchain on their head. So benefits of technology sharing, DFINITY is working on various shared components, such as the next generation EVM, which will probably be based on WASM. I don't know if you've heard about that, like WebAssembly. We're looking at upgrading the P2P networking pieces. The current gossip mechanisms used by Bitcoin and Ethereum are very, very primitive. And for various reasons, we want to improve the broadcast guarantees that the P2P networks can provide. It's important for kind of high-level protocols. And of course, many of the Crypto 3 techniques are directly reusable within Ethereum. So we're hoping that a lot of the research that we've done on protocols and cryptography in relation to performance and scaling, a lot of that work can just be pushed straight across into Ethereum and provide benefits there too. In the end, we think common standards will win out, and we'll get some kind of EVM singularity eventually, right? People are going to want to build on the EVM because it's an open standard and they don't want to go and learn lots of different proprietary formats and systems for building decentralized applications. So that's kind of where we see all this going. This is our vision of decentralization. It's perhaps a little bit different again. We want to see a kind of decentralized cloud. Today, of course, the cloud really exists in quite a small number of very large data centers. And that's a fragile architecture, and there are various other problems with it too. Notwithstanding, it provides good performance, and we want to see a decentralized cloud that's very much more distributed across the world and locations. And one of the aspects of DFINITY's protocols is that they are fundamentally resistant to things like pooling and don't provide any particular advantage with scale. So these sketches here you see relate to DFINITY, sort of consumer DFINITY mining devices under development by String Labs that we hope that people will put in their homes to participate in the network. So we want to see a sort of decentralization of core public services. And this, in fact, was the original objective of the project. So today in Silicon Valley, there's a model that's pursued in which core niches are identified, whether that's chat or social networking or whatever else. And a huge amount of venture capital flows into the leading companies pursuing that niche. And the objective is always to produce a monopoly, right? And eventually you get some kind of consolidation and the market chooses a winner. And there's one dominant company that sits there and becomes an intermediary and reaps huge rewards. But we might imagine an alternative world in which these kinds of critical public services are kind of open sourced, right? They have some kind of DAO-like governance structures that adopt code updates and things like that. And, there are feature bounties put out there and different people propose solutions. This is one of the things that we really want to enable. We actually believe you can produce things like search engines on these blockchain computers, right? Using various techniques we'll touch on later. There are also some advanced services that can run on a blockchain computer that need special kind of features. There's another project I'm involved with called Phi, which is best described as a kind of decentralized version of commercial banking. And it gives out loans autonomously, right? Using randomness that's provided by the blockchain. And it's very important that this randomness is unmanipulable and unpredictable, or the system doesn't work. But so long as it has this randomness, it can sort of play a puppet master, if you like, and it can apply loan validators in a way that allows it to determine if a loan should be granted or not, without obviously being in a position, it's just a dumb algorithm, to evaluate a loan application itself. And it's an interesting system. It produces cryptocurrency units that are backed by loan collateral, just in the same way that fiat money is produced. So you might even call it crypto fiat rather than a cryptocurrency, right? And of course, one of the problems we've got at the moment is cryptocurrency values are so volatile, it's unusable for most financial applications. But with this source of randomness, we can actually produce something much more akin to normal fiat money, which will prove much more useful in decentralized finance. But the key thing to realize is that this ability to give out loans algorithmically and originate money in the process, which is stable and backed by loan collateral, is dependent upon this incorruptible, unmanipulable, unpredictable randomness that's produced by the blockchain computer, made available. So that's one end of the spectrum of applications of the decentralized cloud. At the other end, we have just a sort of enterprise IT vision. And again, this is one of the areas I think where traditional blockchain thinking can be turned rather on its head. We think that the blockchain computer, even though the computation will cost 100x plus more than computation on Amazon Web Services, even more than that, will actually make it possible for enterprise IT to slash their costs very, very dramatically, okay? Because if you look at an enterprise IT system, most of the cost involved in owning that isn't anything to do with computation, right? It's the human capital, And we believe that we can reduce the human capital involved in running these systems. Now, if you were to take a distanced view of the world and sort of look down at the planet from space, and you'd see all these different companies around the world with, network administrators, database administrators, security guys, all that kind of stuff, right? And you'd realize that they're all kind of repeating themselves in different ways. They're all doing the same kind of job. And fundamentally, we all learn in the first year of computer science courses that this principle don't repeat yourself. The whole point of IT is to automate things, right? And yet, we've got all these, millions of IT people around the world effectively repeating themselves and doing the same job. And I think one of the greatest promises of the blockchain computer is that it will remove the need for a lot of these jobs. So, we won't need some specialist database administrator who's configuring master-slave relationships in his MySQL database, right? He won't be managing his backup and restore system because the blockchain computer, of course, is redundant and manages all that kind of stuff. It doesn't go down, right? You don't need to do backup and restore when you've got a blockchain computer, right? So, the key bit of the vision here is that we want to sort of undo a lot of these kind of Rube Goldberg machines that exist and produce a simpler system that abstracts away distribution and things like that and makes it possible to implement the same enterprise IT systems at a fraction of the cost, right? By reducing the human capital involved. And the reduction in costs will occur even though the computation involved is many, many times more expensive. So, you'll have seen this kind of stuff discussed many times, I'm sure. But when you have a blockchain computer, the blockchain provides various properties that make the reinvention of all kinds of existing enterprise IT systems possible. And this has nothing to do with cost, strictly speaking. It's just making them better, right? And a blockchain computer enables you to make sort of autonomous systems, without intermediaries, so you can create systems that are shared amongst many players in an industry. It's unstoppable. There's no servers to fail, right? The blockchain computer only exists as a sort of facet of protocol execution. It's conjured by the protocol, if you like, so there are no servers to fail. It's verifiable. You know what software you're running. It exists in cyberspace. This is another really important one. Because the blockchain computer is created by protocol execution, right? There's no backing server. It's not Amazon Web Services. You have virtual computers, but there's a physical computer behind them, right? But with a blockchain computer, it's entirely virtual. It only exists really as a side effect of the execution of this decentralized protocol amongst clients. And that means it doesn't have any geography. And this is very important because we're moving to a more globalized world, right? And currently, if you want to create a financial exchange, you've got to put it in some geography, right? And then all of the regulations of that geography apply to that exchange, even though your users may be distributed around the world. Okay, and there's a huge problem with regulations and bureaucracy that we're never going to be able to reverse. It's too much. But one of the promises of blockchain computers is that we can move critical shared business logic into cyberspace, right? And then the regulations only fall on the people that are using that blockchain computer wherever they're located. That's a major advance. Of course, these blockchain computers are tamper-proof, right? There's no terminal you can log into, right, to start messing with the files, right? The blockchain computer is really a completely virtual construction, right? You can do things like create shareable systems much more easily because you can have open governance systems. We abstract away distribution, and interoperability becomes much easier because you can co-locate all these different systems on the same blockchain computer and then very easily specify who can access what. So that's the vision. We'll just move on to cover quickly this thing called the blockchain nervous system. This was a sort of recent addition to the kind of vision that was sort of under consideration about the time of the DAO, and then was sort of pushed forward. So the idea is the blockchain nervous system processes proposals. Okay, anybody can submit a proposal. Typically, you'll pay some kind of fee to stop people spamming it. The deposit, if you like, it might be a deposit that's returned if the proposal is adopted, but different models are possible. And the idea is that there is some kind of thing that's separate from the blockchain itself that evaluates the proposal, and the output of the evaluation is adopt or reject. And assuming positive decisions reached and a proposal is adopted, the smart contract component of the blockchain nervous system can use privileged EVM opcodes to execute the proposal. So that enables it to freeze contracts, move tokens. It can even run arbitrary smart contract code that also makes use of these new privileged instructions inside the EVM. So, for example, rather than having to hard fork after the DAO, somebody could submit a contract that makes use of these privileged instructions to perform the necessary manipulations of data to mitigate the problem that occurred, right? So, the thing I should be clear about is this blockchain nervous system is kind of omnipotent within the network, right? It can run arbitrary code that uses these privileged instructions. It can change the economic parameters of the network, like issuance of DFINITYs and things like that. And it can also upgrade the protocol, right? And so if you want an idea about how that works, imagine taking an Ethereum client like Geth or Parity, and then wrapping that in a reverse proxy, right? And of course, you've got this RPC interface, which is like a REST interface, right? But now you're going to access that through the reverse proxy, which wraps it, right? And this reverse proxy is blockchain nervous system aware. So if the blockchain nervous system says, at this block height, right, we're going to change the protocol, and here are the hashes of the different clients, or the installers for the different clients, as the block height approaches, the reverse proxy wrapper simply downloads the installer software from Swarm or BitTorrent or wherever it is, runs the installer, okay? Meanwhile, while the installer's running, the reverse proxy buffers any requests to the RPC interface, and as soon as the new client's running, it unbuffers. So the process of upgrading the protocol is completely transparent to the users of the system. And in fact, the blockchain nervous system potentially can upgrade the protocol as many times as it likes, and there's just no concept of a hard fork in the same way that there is today. There are some special cases if the whole thing breaks where a hard fork may occur, but under normal operation, the protocol can be upgraded pretty much continuously without interrupting the users of the system at all. So that gives you an idea of how different it is to the code is law. And you might say, well, why does it have to go so far? Why give this blockchain nervous system so much power? And the answer is, well, if you can upgrade the protocol, then you can do anything anyway, right? So you might as well make it as easy for it to do as much as it likes, right? So the basic unit in the blockchain nervous system is this thing called a neuron. And you create a neuron by making a deposit of DFINITYs. You get this voting key that you configure into some software that you run on your laptop. And you're going to do this because by participating in governance, you can earn sort of decision mining rewards, if you want to call them that. And your rewards will be proportional to the amount of DFINITYs you've deposited and the number of votes you participate in. And of course, you've now got a stake in the system and a reason to want the blockchain nervous system to make good decisions, right? Because you cannot get the definities you deposited out of the neuron without dissolving it first, and dissolving it takes several months. So if the blockchain nervous system makes a bad decision, right, the markets, of course, will swiftly punish the value of definitives and the value of your investment goes down. So this is kind of how people are staked in it, and the ultimate objective of the blockchain nervous system, I suppose, consequently, is to drive the price of definitives higher on the network, on the market, sorry, and the market price over the long term provides a kind of sort of dopamine that drives its actions. So most people, of course, are extremely lazy or possibly unqualified to vote. Like, not many people actually want to look at the low-level protocol proposals that'll come in and try and decide how they want to vote themselves. They're just not qualified, or haven't got the time. So you can configure your neuron for different topics to vote automatically depending on the output of other neurons, and we call them follow relationships, but a follow relationship can be arbitrarily complex, right? It could just be you're waiting for some other neuron in a priority list, and you're going to follow it, but it could also be that you're going to look at the votes for a group of neurons and assign weights to each of them and so on. And typically the neurons you'll follow will be kind of respected and well-known community members. It could be a core dev, it could be the foundation, it could be a Reddit pundit who puts the addresses of one of his public neurons at the bottom of his Reddit post, right, to encourage people to follow him or her. But it could also be a traditional IT system. So, trivially, you might imagine that there's a Bayesian classifier that looks, receives some kind of feedback on previous decisions, right? Looks at new proposals in the context of them and makes some kind of judgment on whether the proposal is likely to be a good decision or a bad decision. And it's unlikely that people would want to trust this thing entirely, but you could imagine incorporating the input from this Bayesian classifier into your follow relationships, into some score-based follow relationships. So it's a kind of hybrid AI system. And you've got this neuron client software where you can browse proposals, you can see how your neuron has voted, you can drill down, you can look at other neurons and see how they voted and so on. And of course you can configure your kind of follow relationships. So, I mean, if we sort of just wanted to kind of create some key points on the blockchain nervous system, we'd say, first of all, it provides some kind of making decisions by applying some kind of algorithm to the sort of wisdom of crowds, if you like. Traditional AI can be integrated via neurons, so it's a platform for developers of traditional AI to sort of further automate the governance process. These neurons cascade to make decisions, and that's an interesting aspect of it, right? And it's non-deterministic too, because timing's involved, right? The objective of the blockchain nervous system is really just to drive the market value of definitives, right? Because people have deposited definitives to create a neuron. The market reaction to decisions is a kind of dopamine. You hope that people will filter that to some degree because the neurons are locked up over the long term, so they're not looking for short-term movements. And the thing kind of learns, because relationships can be outdated. So if you can imagine that, some kind of guy appears on Reddit, a sort of demagogue, populist kind of guy, and he comes out with some kind of campaign, make DFINITY great again, or something like that, and he says, here's the address of my neuron, follow me, and so on, and then eventually he gets lots of people to follow him, and then there's some really stupid proposal that goes in, and he gets it adopted. If the markets look at this and say, hey, this DFINITY system's gone crazy, right? It's, following this kind of populist demagogue, and it's now adopted this ridiculous proposal, almost certainly the markets will punish that behavior, and the price of the definitors will go down, and those people that had configured their neurons to use the output of his neuron as input will probably unfollow him pretty quickly. So in that sense, it learns. What's very, very important is that these follow relationships, though, are unknowable, right? Because they're only configured in this client software that runs on the edges of the network, right? The follow relationships are configured into the client software that runs on people's laptops, for example, right? And so if you have 20,000 people running neurons, the only way of really understanding how the blockchain nervous system will make a decision would be to hack their computers somehow and download their follow relationships. And without that information, you can't really get any insight into how it's going to make a decision or why it made previous decisions. And this is important, of course, because otherwise you could just analyze these relationships and you could identify sort of key people, and you could try and blackmail them or bribe them, or or moreover, perhaps even more likely, imagine that there was some kind of system on the blockchain computer that the blockchain nervous system decided was a miscreant system and it wasn't good for the value of definities, and it froze that system, right? If the owner of that system could identify who had perhaps tripped the decision in that cascade of neurons, they might want to sue them, or a government might want to prosecute them for something. So it's very important that this thing's like a black box. You can't see how it's made a decision, and you can't know how it'll make a decision. So it's a kind of, there's a few posts on the DFINITY network blog. If anyone's interested in the blockchain nervous system, it's a good place to find out more. So the last thing I wanted to explore was a crypto 3 technique, because the original objective of DFINITY was to create this infinite, highly performant blockchain computer, and naturally, one of the first things you need to do is address how you're going to reach agreement and consensus, and also produce these random numbers that are used to drive other pieces of the system and other protocols. And you see a lot of blockchain research at the moment talking about using traditional BFT consensus, right? Byzantine fault-tolerant consensus protocols from the distributed computing branch. And this does something in a very different way to those protocols. So those protocols require point-to-point connections, right? Firstly, you can try and hide your processes behind Tor addresses and things like that, but it doesn't give you very good performance, right? So you're creating the risk that your network can be DOSed, and the other problem is, of course, that they don't scale well with the number of participants, because the number of messages they produce are quadratic in the number of participants. So they're kind of useful for some kind of 50 node network that might be used for settlement between two banks or something like that, but they're not suitable for public networks. So what we sought to do is create similar levels of performance in a way that only required a broadcast network, P2P broadcast network, which is suitable for public networks, and doesn't degrade the more participants you have. So we want to be able to have 1 million participants if necessary. And we also want to be able to create this randomness. So threshold relay is like this sort of foundational technique we use. Now, threshold relay itself just produces this sort of incorruptible, unmanipulable, unpredictable randomness, and we'll see why that enables other things in a moment. So we use a special signature scheme called BLS, which is a threshold signature scheme, and it's something that you'd call a unique deterministic signature scheme. And what that means is that given a private key, right, and a public key, and some message, only a single output signature is possible, right? Only a single output signature is possible. So we can use this as a random number generator, right? Because by the security properties of a signature scheme, can't be possible to predict what the signature output on a message will be, because otherwise it wouldn't be secure, right? And BLS gives you this property, and it also gives you this property with a threshold signature scheme. What that means is if you have, some number of processes in your threshold signature scheme, that group of processes can have a public key, right? And they can all collaborate to sign a message. But it's not interactive. All they need to do is create what's called a signature share on the message and broadcast it. And the beautiful thing is that you only need to collect the threshold of signature shares to generate the output threshold signature for the group. But that threshold signature will always be exactly the same whichever subset of those processes sign, right? So imagine if you've got a group of 400 processes, right? They've got a single group public key, a message is provided, right? And the group, all of the group members produce a signature share on that message. If the threshold is, say, 201, it doesn't matter from which 201 you collect signature shares, right? When you combine them to produce the threshold signature, it will always be exactly the same. And that's what it means, that's what unique and deterministic means. If you think about it, this is an incredible opportunity because it means that those 400 processes have produced a random number that they can all agree on without running a consensus protocol. Furthermore, if that group was a subset of a much larger set of 1 million processes, so long as everybody knew the public key of that group, everybody could agree that the signature the group produced was correct, because only a single signature on that message is going to be valid for the group's public key, right? So the entire network can agree on this random number without running a consensus protocol. And as you might imagine, this random number might be a stepping stone to other forms of agreement. So just visually, we imagine a vast peer-to-peer network of mining clients. And these mining clients are registered on the ledger. So, they're each going to have a public key, and, they've created their key pair and participating in the network after depositing some number of DFINITYs. It's a bit more than that, actually, but it's a bit like a kind of proof-of-stake scheme. Except in DFINITY, each mining client has an approximately identical role, right? They're all expected to provide a roughly equivalent amount of computational capacity. So you can imagine that these mining clients are assigned to groups randomly, right? So in fact, as this random sequence of numbers proceeds, there's going to be a function on these random numbers that assign these mining clients, these processes, to groups, right? And when you're assigned to a group, you then run this DKG scheme, it's a distributed key generation scheme, right? To set up your threshold sharing, and so your group can produce signatures. And if and only if, this runs asynchronously, if and only if your group successfully runs the setup, it registers its key on the ledger too, right? So the blue group has just set itself up, and here we have the pink and green groups running their DKG processes, and this is happening asynchronously, independently of blockchain progression, so nothing's being held up. Obviously, you can imagine that group keys go live in epochs, which might be, if you've got a block time of like 5 seconds, the epoch might be a week. Once a group has been selected by the randomness and told that it can set itself up, be given some large number of blocks to perform the setup, and it's quite expensive, and that happens independently. And if, and only if a group succeeds in setting itself up inside the allowed number of blocks, it registers the group public key on the ledger. So we're going to end up with this set of groups, right? As regards the blockchain itself, so at some height, h, there will of course be a current group. Here we've got the pink group. And this group, it signs the previous group's signature, right? So, whatever the output, the threshold signature of the output by the previous group was, the new group will sign it, right? So, once you've created a new signature, of course, you can use that also to select the next group, right? So you just modulo the signature by the length of the list of groups, right? And you've got you just randomly selected the next group, right? And then that next group signs the signature of the previous group and so on ad infinitum. And you get a kind of sequence of groups. So let's look at it like this. Here we've got a group at h-1, it's produced a signature. The signature is moduloed by the length of the list of groups. This selects this next group at h. Each of the members of this group at h broadcast a signature share on the previous signature. You can then combine those to produce a new signature, which then selects the next group at h+1, right? And this process is entirely deterministic, and it's unmanipulable. There's just no way you can manipulate it, because by the properties of the cryptography, every single signature is unique and deterministic. There's only one valid signature that's possible on the previous group's signature. So what, of course, you get is this thing called a decentralized VRF, a decentralized verifiable random function, which is a sequence of random numbers that's deterministic, verifiable, and unmanipulable, right? And the next value in this VRF is released on the agreement of a threshold of the current group. And this produces another property, which is that it's unpredictable, right? This is another very, very essential property for things like phi. So Donald Knuth said, random numbers should not be generated with a method chosen at random. And I think DFINITY will create the world's first completely trustworthy decentralized VRF, which people can use potentially outside of the network as a random beacon. And this unmanipulable randomness is very, very useful for a number of different purposes. So firstly, within DFINITY, we apply it within these various other protocols that make it possible to scale out the network because we're trying to create an infinite blockchain computer. We're going to explore this thing called probabilistic slot protocols next, which will show how to build a kind of blockchain inspired by Nakamoto's design on top of threshold relay. But there are a bunch of other techniques we use, like validation towers, validation trees, I think, or USIDs, or unique state copy IDs, all of which use this and depend upon this randomness. And if you think back to the introduction I gave, one of the driving objectives behind DFINITY when the work began in 2015 was thinking about how we could create a search engine on top of the blockchain computer. Now, as you know, search engines need to perform searches very quickly, or the users get bored and won't use it. And certainly, even with this probabilistic slot protocol design I'm going to show you, it's not quick enough, right? 5 seconds or whatever is not fast enough. So what you can do is you can apply the randomness with techniques like a thing called lottery charging, where if you've got to pay for the search, you pay 1,000 times what it would normally cost, and then the miners provide the results straight away, and then they see if the randomness allows them to actually check this transaction, if you like, right? Cash this transaction in. But that would only happen 1 in 1,000 times, right? So just multiply the fee by 1,000 and then only have it actually be applicable 1 in 1,000 times. Lazy validation is a similar kind of technique. So randomness really, really is incredibly powerful. And I think we'll see eventually, there'll be theoretical computer science results that show you just can't do this kind of stuff without randomness. And if you look back and study, for example, Nakamoto consensus, you'll notice, of course, that it's got a kind of random number generator, right? Everyone's racing to solve a current puzzle by brute force, and the nature of that is that because the first person who finds the solution has to broadcast it to get their block in, it's a kind of random number generator, right? What you're doing is having everybody race to solve the puzzle, and then whoever solves it first by luck is elected a temporary leader, and they can broadcast a block, right? But it's all about random numbers, really. We found as well that when you start looking at more advanced decentralized applications, Phi is only just one example of the applications we're looking at. Actually, if you want to do this kind of stuff, you also need this unmanipulable, unpredictable source of randomness. So it's really a very important thing. So quickly, before moving on to the probabilistic slot protocol, let's just consider the fault tolerance of this system. So just by way of example, let's imagine that we have a network of 10,000 processes. 3,000 of those processes are faulty, which is already, in the kind of network that we envisage, very unlikely. So with 3,000 faulty processes, 7,000 correct processes, the group size is 400, right? The threshold is 201. So you can use hypergeometric probability to calculate, if we've got a random group of 400, what is the probability that 200 or more are faulty, i.e. that the group won't be able to produce a signature? Right, and the threshold relay will stall. It's 10 to the minus 17, right? Which is, clearly a huge number and not something we'd ordinarily worry about. But you can increase the group size, and this ramps up really quick. So, at a group size of 600, I don't know what it is, but it's some huge number. Communications overhead. So. Again, let's go with the group size of 400. When a group is selected, and all of the group members have got to create signature shares, so that these might be combined to create a threshold signature. They're all going to broadcast some kind of message. The message is going to have the ID, like some kind of hash of their public key. It's going to it'll have the signature share will be 32 bytes, the signature on the communications, and so on. So 84 bytes, right? So if you have 400 of these processes broadcasting a message of that size, okay, the maximum communications overhead is 34 kilobytes. But of course, in a P2P network, once the threshold signature itself has been produced, the nodes will stop relaying the signature shares. So in practice, you're looking at about 22 kilobytes being broadcast across the P2P network in order to produce the next unmanipulable, unpredictable randomness. Right? So the communications overhead of this thing is absolutely tiny, right? Able to produce the next random number with very little overhead at all. And all of this is without running any kind of consensus protocol, right? Just using cryptography. Not a consensus protocol on the site. We're able to produce the sequence of random numbers, right? In a way that is very, very difficult to interrupt. And also very high performance. So we've got various applied cryptographers working on libraries to optimize BLS, and these signatures can be produced in a few milliseconds as well. You can combine all of these shares in just a few milliseconds. It's incredibly efficient. So now we've got this mechanism where we can relay between these groups and produce this randomness. How can we extend that to produce what we commonly think of as a blockchain? And so now we're going to create this thing called the probabilistic slot protocol. So this is what I want you to imagine. At each height, right, in this relay, at each height we're going to use the randomness produced to order all of the processes. Now this is very easy, of course, because the processes are registered on the ledger. So we can just use the random number produced in numerous ways to produce a random ordering of all the processes. So here we are at block height h-3, and we've got a list of processes, and that's what it means. I've got process 4243. This is just some nonsense made up ID, right? So it's a priority list of processes. So the highest priority processed at this height is P4243, the next one P3911, the next one P0392, and so on. But if there's a million processes, the list will have a million entries, right? So we're doing that h-2, we're doing it h-1, we're doing it at h, and so on, ad infinitum. Every single height, we are creating an ordered list of processes. Now, we can also think about those processes being in slots, right? So if you're the first process in the list, you're in slot 0. If you're the second process, you're in slot 1, and so on, right? And of course, you're probably seeing where I'm going to go. It's like a forging slot, right, for creating a block. And we can assign points. So we can say, you know, if you produce a block and you're in slot 0, your block will be worth 1 point. If you produce a block and you're in slot 1, it's worth half a point. If you produce a block and it's in slot 2, it's worth quarter point, and so on, right? So now we've got a way of scoring blocks. And we can also introduce relay delays and things like that. This is an optimization, not a safety thing. So we could say that, let's say the block time's 5 seconds. If you're in slot 0, you can you know, produce your block after 5 seconds and everybody will relay it. If you're in slot 1, you can only produce your block after 6 seconds. If you produce it before, nobody will relay it. And there are various reasons this makes the network go a bit faster. So as a first kind of try, we can clearly create a blockchain that is formed by scoring the blocks. Will eventually converge, and here we can see we've got 2 different chains that are rooted. They've got a common root at you know, h-3. We've got the green and the orange chain. The pink chain died. And at height h, we've got the 2 chain heads. The orange chain has gained 3.5 points since the common root. The green chain has gained only 3 points since the common root. So if you were a correct process in slot 0 at h+1, if you were a correct process, you would choose to build on the orange chain, right? Because it's got 3.5 points since that common root at h-3, whereas the green chain has only got 3 points since the common root at h-3. So the orange head is the best parent, and a correct process would build on that one. And that's, you know, if we assume that there are more correct participants than faulty participants, then, you know, we should converge. But, of course, we've got the usual problems that we see in Bitcoin and other kind of derivative proof-of-work schemes. Selfish mining attacks are possible, right? The adversary can sort of withhold his block, right? Wait till the correct process at the next height is mined on a lower scoring one and then reveal his block, and so one of his guys in a lower slot can gain an advantage. So there's all kinds of selfish mining attacks that are possible. That's no good. There's also this thing called nothing at stake. I don't know, did you guys like follow proof of stake protocol development? So that exists too, and these are things that bedevil just about every proof of stake kind of blockchain, and indeed even proof of work blockchains when you reduce the block time. So what is the solution to this? And of course, it turns out that threshold cryptography provides us with a very, very nice solution, okay? So we can have these threshold groups notarize, okay, blocks that appear at their height, right? And we can require that when you produce a new block, it can only reference a previous block if it's been notarized, right? So, you know, we get to some height, h, right? And first of all, only blocks that reference a notarized block at h-1 are valid. And secondly, anybody at this height h must quickly broadcast their block. Otherwise, the group won't notarize it, right? And their block is going to be dead. So there's no chance, there's no use in withholding blocks anymore, because if you withhold your block, it's not going to be a block because the group won't notarize it and nobody can build on top of it, right? So we remove the ability of the adversary to withhold blocks. So let's just imagine then what happens with the new system. So here we go. We've got the pink group has been selected by the previous threshold signature. And they all start their stopwatches. Of course, they don't have perfectly synchronized clocks, but that's okay. They all start their stopwatches and they're going to wait for the block time. I'm talking about a block time of 5 seconds here. While they're waiting for the block time to expire, they create a priority queue of blocks that want to be notarized. So going back to our previous example, there was the orange there was this orange chain head, and it would obviously have 3.5 points relative to this base score, and the green chain would only have 3 points, so the orange chain head would be at the front of the queue, right? It would be at the front of the queue. And once the block time expires, we enter this very, very simple, super simple. It's slightly oversimplified, there are some missing pieces, but you'll get the idea. Super simple algorithm. So each member of the group looks at the queue, and it withdraws the highest priority block that's waiting, and it asks the question, has it signed a high scoring chain, right? If the answer is no, and that process's slot is ready, it just broadcasts a signature share on that block, right? And it goes back around again, withdraws the next highest priority item from the queue, and asks, has it signed a high scoring chain? Now in normal circumstances, of course it will have, because it'll assign the slot 0 block that was waiting first, and so it just goes back to waiting for a higher priority chain head, which in normal circumstances won't arrive. And they keep on doing this until they detect that their group has successfully created a threshold signature on at least one block. It's possible they do more than one, but it's unlikely, right? And as soon as they see they've created a threshold signature on at least one block, they then broadcast a signature on the next chair and they relay. And so what we get is fair mining. Selfish mining doesn't work, and we get extraordinarily fast convergence, right? Forks collapse very, very quickly indeed. And we address all of these kind of issues with selfish mining and nothing at stake. And even better, there's a special case, there's an optimal case which occurs in normal operation that can give you overwhelming finality in two blocks and one relay if you can rely on the broadcast assumption. And you heard me mention earlier on that we're working on the P2P networking layer, and of course this is one of the reasons for it. Let's assume that at H, right, we're at H plus 1 now. At H, there's no alternative chain head, right, or even partially signed chain head visible, right? But we know, right, for a viable chain head to exist, it must have been shared with at least some correct processes, right? Because you need to get some the adversary can't get this stuff signed on his own, right? By the laws of probability. So even if the adversary can add some number of signatures himself, in order to have a chance of getting this thing notarized, he has to share it with at least some correct processes, right, to get their signatures. And the correct processes, of course, follow the protocol, and they will broadcast the block they added their share to. And yet it's not visible, right? And now we're at H plus 1, and H plus 1 has notarized a block, and it's relaying to H plus 2, and basically the trap is shut, right? It's too late for any alternative chain head to appear at H, right? So we can say that since no fork is possible at H, that there's an overwhelming probability that the block at H is final, right? So with a 5-second block time, that gives you expected finality of 7.5 seconds, right? And I think in practice we'll see something much less, because we're going to create two different networks, one for China and one for the Western world. So you don't get the slowdown that's involved with the the Great Firewall. So I really believe we'll probably see finality and sort of expected 3 seconds or something like that, right? Huge speed up over what we see today. So one of the nice things about this protocol is it's difficult whenever you see something for the first time, but it's actually very simple. And if you think back to Nakamoto consensus and Bitcoin, one of the great advantages of it was that it was a simple system, right? It's quite easy to understand once you've understood some core principles. And threshold relay and probabilistic slot protocols are similar in that respect. They also provide a fantastic means to do secure and high performance SPV-style light client stuff, right? Because without getting into the details, if you're a light client and you know the Merkle root of the set of groups, right? It's going to be possible for you to receive some headers, just block headers, and validate that that's been signed off by a valid group, and then you can go back some number of blocks and probabilistically convince yourself that some kind of proof is valid, right? So it can kind of out SPV Bitcoin, which is rather nice, right? So yeah, this is going to be in threshold relays, a sort of foundational technique, and it'll be in this copper release, which is the first one coming. So you've got this big speed up, from sort of 60 minutes in Bitcoin, 10 minutes in Ethereum, down to just a few seconds. Once we get rid of the Poisson distribution, we can also increase the capacity, right, of the network enormously too. Because one of the problems of proof of work is that when you reduce the block time, miners are given a very strong incentive to produce empty blocks. And in fact, about 50% of the blocks, I believe, in Ethereum are empty right now. And the reason is very simple. If you're a miner, you don't want to delay producing your block, right? So if you have to choose between a bunch of available chain heads, you're going to choose the emptiest block because you have to do less validation work before you can start mining, right? So it's more efficient. So therefore, if you're producing a block, you'll prefer to produce an empty block because somebody will prefer to build on you, right? Because they don't have to delay, right, by validating your transactions first. So that's what happens in extremis, but once you get rid of the Poisson distribution, those kind of problems go away, and you can give people a fixed amount of time to incorporate transactions into a block and validate them without economically disadvantaging themselves. So just by this simple trick, of course it's scale up, not scale out, you can greatly increase the capacity of the network, which is why, you're seeing not only are we going to increase the speed over what you see today by sort of 50x plus, we're also going to increase the gas available. Finishing up, just look at quickly the kind of thinking on scale out and how that kind of stuff works. I think within the cypherpunk community, there was a lot of work over many years to produce just this cryptocurrency thing, Bitcoin. It took a long time, and lots of different techniques were examined, and it kind of got this kind of ingenious thing where you got everyone kind of expending electricity to try and solve the puzzle by brute force so they can get elected a leader and add a block to the chain. But when you want to build a more advanced system, you have to sort of stand back a bit and structure things a bit better. And if you look at proof of work blockchains, they muddle a lot of different things up. You've got Sybil resistance, right? Which is the mediation of participation to stop an adversary overcoming the fault bounds of the network. You have to burn electricity to participate, which of course costs money. You've got the state storage. All of the state is carried in the actual Bitcoin blocks themselves, right? The random number production, which is linked to the Sybil resistance, is what gives you the consensus, and then you've got the validation and so on. It's all mixed up. So, what DFINITY does is it sort of breaks these things into layers. It's a bit more, like TCP/IP or something like that. It's more structured. So this is kind of very high level view of the DFINITY architecture. At the top level, you've got the consensus layer, which is a threshold relay chain. And this thing only stores a state root. So one of the things, hopefully, if we've got enough time, you'll see in the first copper release of DFINITY, there's no notion of like the transactions being logged, right? This is an absurd idea, right? All that matters is that the network makes sure that the state root, the state that's recorded, only undergoes valid transitions, right? It should never be the case that if you want to validate the state, you have to actually go back and reapply every transaction since Genesis. This is a completely crazy idea, right? You've got a top-level threshold relay chain that's producing this randomness, and it's storing the state root. The state root is, the root of a kind of Merkle tree-like structure, okay, that's produced by a thing called a validation tree, right? And a validation tree has a thing called a validation tower at each node, And these are driven by the randomness. And if you go to the DFINITY website, there's like an FAQ, and if you go into the technical section, you can see descriptions of exactly how validation towers and so on actually work. But it turns out that you can create a single scalable validation layer if you have this incorruptible, unmanipulable, unpredictable randomness, right? And this is why it's so important. And this thing proceeds asynchronously, so it can scale to any size you need, right? And then down the bottom, we have the storage shards, right? And the storage shards are pushing up data and state transitions to the lowest nodes in the validation tree, right? Which validate the transitions. And then when they validate the transitions, higher level nodes actually produce a sort of digest from their transitions that are validated and so on until you get this single digest out the top. So this validation tree thing kind of produces for a decentralized network, does something for a decentralized network roughly akin to what a Merkle tree does, for large data sets, right? And I believe the only way this is ever going to be possible is using, with this kind of source of randomness. And it's very important if you want to create an infinitely scalable blockchain computer that you have this global validation there. And a lot of people you see propose solutions that just don't work. They say, okay, what we're going to do is we're going to have lots and lots of different blockchains, right? And they're going to communicate with each other. And you can create some output on one blockchain and somehow that'll be imported into another blockchain. But that doesn't work because you're only as strong then as your weakest link, your weakest blockchain. And if somebody manages to take control or subvert one of these blockchains, it can export bad data to all the other blockchains, right? So it's not actually possible to break it up in that way. You need to have a single global validation there, right? And you need to make that single global validation layer run in a way that is sufficiently asynchronous that the shards can all proceed at their own independent speeds and aren't delayed by the slowest piece of that layer. And this is all possible with randomness. So that's pretty much it from me. There's the release we're working on is the copper release, and it's going to have this threshold relay and probabilistic slot protocol chain. It's going to have the blockchain nervous system, security deposits, hopefully state root only chain, which means no transaction logging necessary. The release following that's called Zinc, and it has some features enabling private chains, private DFINITY chains, to host smart contracts that make a single call into a contract on the public chain, which means you can do interesting things like you can integrate different private chains via financial exchanges and things like that. And then Tungsten will begin to introduce the scaling techniques. If anyone is interested in BLS, we've got various implementations, super optimized implementations that are online now. And that's it. Yeah, thanks.